Welcome back to another explainer. So, have you ever actually sat back and wondered how computers really understand the code we write? I mean, we type out these nice, human-readable logic statements in Python, Java, or C++, but the machine, well, it only speaks binary. And the bridge between those two worlds? It's not magic, and it is certainly not just a basic dictionary translation. Underneath every single modern programming language is a hidden, highly structured mathematical system. It takes our human logic and translates it into flawless machine execution. Today, we're uncovering those hidden systems by looking at context-free grammars. We're going to completely strip away the abstractions and look at the bare metal of how code goes from simple text characters on your screen to a mathematically sound format that a computer can actually execute without a single hesitation.
Okay, let's dive right into this. Here is our roadmap for today. We'll start with the Chomsky hierarchy, move into exactly what context-free grammars are, then look at leftmost and rightmost derivations. After that, we'll tackle identifying grammar ambiguity, explore simplification using CNF and GNF, and finally, wrap up with compilers and programming languages.
Let's kick things off with Section 1, the Chomsky hierarchy.
Before we can really understand specific coding grammars, we need a map of formal language theory. Back in the 1950s, the linguist Noam Chomsky categorized all formal languages into a spectrum, going from type 0 all the way down to type 3. Up at the very top, type 0 is completely unrestricted. That's basically anything a Turing machine can compute. Down at the bottom is type 3, which covers regular grammars. Now, you actually use type 3 every single time you write a regular expression to search for a string of text. But regular expressions have a fatal flaw when it comes to programming. They don't have memory. They literally can't count or balance nested structures. So if you open 3 parentheses in a math equation, a regular expression has no idea it needs to close 3 parentheses. That is exactly why programming languages live snugly right here in the middle at type 2, which are context-free languages. Type 2 languages are processed using push-down automata. That just means they have a stack memory. They can remember exactly how many brackets you've opened and ensure every single one gets closed properly.
Which brings us to Section 2, Context-Free Grammars Explained. So what exactly is a context-free grammar, or CFG for short? Well, think of it as the mathematical skeleton of a programming language. It's basically a set of recursive rules that dictate exactly how abstract variables can be substituted with terminal symbols, which, by the way, are just the actual raw characters of your code. It's kind of like a highly rigorous game of Mad Libs for machines. A CFG provides absolute, unbreakable rules saying something like, a statement can be an if clause, followed by an expression, followed by a block of code. And the context-free part? That's absolutely crucial. It means the rules apply exactly the same way, regardless of the surrounding context. A while loop is a while loop whether it's right at the beginning of a file or nested 50 layers deep inside some function. Without these strict recursive rules, a compiler would just look at your source file as a meaningless, chaotic jumble of text. The CFG brings that necessary, predictable order to the chaos.
Moving right along to Section 3, leftmost and rightmost derivations.
Let's look at how this builds in practice. When analyzing derivations, we're essentially watching the grammar rules unfold in real time to build what's called a parse tree. The parser takes a root rule and just starts substituting variables until it perfectly matches your raw code. But here's where the theoretical mechanics get incredibly practical. Does the parser expand the leftmost non-terminal variable first or the rightmost? Well, that choice dictates the actual physical shape of the resulting syntax tree. And why does the shape of the tree matter? Because the tree determines the order of operations. Think about a simple math equation in your code, like 2 plus 3 times 4. If the parse tree carelessly builds out the addition branch before the multiplication branch, the machine is going to evaluate 2 plus 3 first, get 5, and multiply by 4 to get 20. And as we know, that is entirely wrong. By strictly controlling the derivation rules, developers ensure the syntax tree is built correctly every single time, preserving the exact mathematical integrity of the logic you just wrote.
Next up, Section 4, Identifying Grammar Ambiguity. Now, I want you to really think about this for a second. What happens when our grammar allows 2 entirely different parse trees for the exact same line of code? Well, when a grammar allows a single string of code to be successfully parsed in 2 distinct ways, you've hit computational ambiguity. And trust me, ambiguity is a computer's absolute worst nightmare. A classic real-world example of this is the infamous dangling else problem. Imagine you write a nested if statement, an if inside an if, and that's followed by a single else. Which if does the else actually belong to? The inner one or the outer one?
If the grammar is ambiguous, the compiler goes ahead and generates multiple valid parse trees. It literally doesn't know what you want it to do. It might attach the else to the outer if when you actually meant it for the inner one, which leads to catastrophic logic bugs in production. Identifying and resolving these ambiguities is one of the most critical steps in language design. Remember, a compiler can't just guess your intentions. It needs absolute mathematical certainty.
That takes us right into Section 5, Simplification with CNF and GNF. To prevent that ambiguity and keep parsing speeds blazing fast, engineers rely on something called normalization. They take these complex grammar rules and simplify them down into highly predictable structures. The two heavyweights here are Chomsky normal form, or CNF, and Greibach normal form, GNF. CNF is incredibly elegant because it forces every single grammar rule into a strict binary step. A variable can only ever be replaced by exactly two other variables or exactly one terminal character. No more, no less. And this binary branching is huge because it makes the resulting parse tree perfectly predictable and dramatically limits the search space the algorithm has to traverse. In fact, it mathematically guarantees that any string of length n can be parsed in exactly 2n-1 steps. By simplifying the grammar into these normal forms, language designers strip away all the bloat. They create a lean, mean parsing machine that never stalls out when reading your code.
Finally, let's tie it all together with Section 6, Compilers and Programming Languages.
Okay, let's connect all these dots. How does all this theory actually compile your code today? Well, the tools you might have heard of, like Lexignac or modern equivalents like ANTLR, they're built entirely on these context-free grammar principles. When you hit Build in your IDE, the compiler's syntax analyzer uses a CFG to process your text file. It reads your characters, checks them against those rigorous grammar rules we just talked about, and constructs an abstract syntax tree, or AST. That tree is the clean, unambiguous representation of your logic. And once that AST is built, the compiler can confidently optimize it and translate it straight down into the raw binary or assembly language the processor actually needs. So the CFG is the exact engine driving the syntax analysis. It's basically the ultimate gatekeeper, ensuring the code you wrote is valid, unambiguously structured, and ready to be compiled.
Which leaves us with this final thought. If CFGs define how machines read our code today, what grammar will define how AI writes its own code tomorrow? It's a pretty fascinating question, right? Because as large language models begin generating and compiling their own complex logic systems, the underlying rules of formal language theory are going to be put to the test in entirely new ways. Understanding these frameworks means understanding the very foundation of human-machine communication. As computation evolves, mastering these mechanics really gives you the key to what comes next. Thanks so much for joining me for this explainer, and keep learning.